Well, welcome to lesson 27 of this Arduino C++ course, and this is part 3 of our look at serial communication. And today I'm going to be looking at how we send multiple bytes, in other words, how to send an integer or a long, breaking it down into bytes for transmission. And we're also going to be looking at error checking and packet formation. So let's get started. Now, the workbench today is a little bit boring because I'm going to be concentrating on communication between these two UNOs. However, the code could be changed so that it's between a couple of megas or a mega and an UNO. However, although we're looking at the basics of communication between the boards at the moment, we've just got two wires. Why would you communicate with two boards less than an inch apart? However, the lessons we learned today, these wires could be replaced by a Bluetooth module. So you could be transmitting in the same way over Bluetooth. Alternatively, we could be swapping these out even for fiber optics or an RS485 communication so that we can communicate over large ranges. Also today, I'm going to be looking at data corruption, how we put data into packets, and adding checksums, and those sort of things are useful even for these MP3 players. These MP3 players require serial communication, but they also have properly formed packets to send the data, and they require checksums. Now, if you're wondering what all that's about, let's take a look at the code. So as always, there is the link below the video that will take you over to the Digital Towns lessons page. And if you then scroll down to the lesson 27, you will then find the circuit diagram and the code that is downloadable. Clicking on the circuit diagram brings up the larger version. Today, I'm going to be just connecting between the two UNOs. But if you change the circuit to the, add the ESP32 in, the Arduino Mega, do a change between all of them, whichever you want, the lessons that we're going to learn today in communicating the data will be the same for all of these different systems. Now, moving over to the Arduino IDE, as in the last lesson, I will be looking at two sketches at the same time. There will be an A sketch and a B sketch. Going back to the webcam, the A sketch will be running on this Arduino UNo. I think this is one of the originals, and it will be transmitting to this second Arduino. Now, for today's lesson, I will just be transmitting from this Arduino to this Arduino. In the next lesson, we'll start to look at how we can arrange timings between the Arduinos to send data backwards and forwards. So looking at the first sketch, I'm going to continue from the last lesson where I ended with a problem with sending the value of an integer. Now you can see at the moment that this left-hand side, that integer has now increased in value and it's sending values in the 940 range. Whereas on the receive side, I'm back down at 180. Now, if I restart this sketch on the left, we'll see what's going on again. So I've restarted the sketch, and as you can see, the values are balancing out: 249, 250, 251, 52, 53, 54, 55. Problem goes back to 0 while this continues to increase in value. And the problem is that you cannot send an int. We have to send the values 1 byte at a time. So what we're going to look at today to start with is how we do send an int value by breaking it down into 2 bytes. So looking again at the code, in the sketch that is going wrong, I am trying to serial write the value of counter. Now, counter is that integer And if I bring in my faithful calculator, let's just move it over. This is an int, so we've got 8 bits and 8 bits, so 2 bytes. And unfortunately, it's only sending over the low byte. So it's sending over any value in these last 8 bits, but it's completely removing the high byte. Now, thankfully, within the Arduino IDE, there is a solution to this, and we have two functions, high byte and low byte. Now, if I go over to the Arduino reference, the reference for high byte means that it will work with an integer, and it will take the high part of the integer value. So bringing back the calculator, the high byte is the highest value byte, whereas the low byte is, if you like, the lower value part of the number. So now, instead of trying to send the whole value in one go, that doesn't work, in this sketch 9a, first of all, I'm going to serial write the high byte, then I'm going to serial write the low byte. Now that's just the order that I've done them in. Some people send them in the opposite order. It really doesn't matter, providing that your code is ready to receive those values. Now, if I now bring up the serial monitor, we can now start to see that the system is breaking up the bytes for transmission. Now I'm just going to stop the scrolling there just to highlight what's going on. So we get the value 254. Now that has a high byte of 0. The low byte has the value of 254 because a byte can hold a maximum value of 255. I've got the binary values there just so that you can see what it would look like. So we've got the whole number, then I've got the high byte binary and the low byte binary, just so you can actually see the individual bits. Now, again, with the value 255, the high byte is 0, the low byte is 255, and we can see that now that our low byte, that full line of ones, our high byte is still a 0, but as we get to 256, our high byte now has a value of 1 and the low byte has a value of 0, and that gives the original binary value, and then we've got our high byte and our low byte that is being transmitted. Now obviously I'm now sending over these 2 bytes, and my receive sketch is receiving the 2 bytes. If I just stop the scrolling for both of these, you can see that I am sending over a value of a high byte of 1 and a low byte of 158, and now I'm receiving a 1 and a 158. But of course the issue is I now need to put those values back together. So now in sketch serial V9B, we're going to stick those 2 bytes together and turn them back into our int. Now to do that, I am going to create an array. This is a 2-element array, and it is a byte array. One of those elements will store the received high byte, the other element will store the received low byte. I also need to create another variable, the incoming byte position, because this is going to keep track of whether I am on the high byte or the low byte. So coming down to the main loop, very, very simple. We're just looking again, has something been received? Is there something available on serial 1? And if there is, that's going to be stored in a temporary byte called incoming byte while I decide what I'm going to do with it. Now, what I do with this value is I put it into one of the elements of the array. Now, because incoming byte pos will start with 0 and I'm transmitting the high byte first, when the first byte comes in, I want that to go into the high byte position. Then what it's saying is, if we're currently storing it in the high byte position, that's element 0, then change the value of incoming byte position to 1 so that it is ready for the next byte to arrive. Otherwise, set it to 0. Now, what it's then done, it has received that information. So the first byte went into the high byte. The second byte goes into the low byte. And then, as well as changing the value, I've got my value, my counter, which is my integer up here. And to recreate my integer, I'm going to take the high byte and multiply its value by 256. And then I'm just going to add the low byte to it. And I'm going to serial print that out. Now, if we take a look at the calculator, looking at the calculator, we've got the high byte and the low byte. This value, the maximum is 255. So if we go 1 over, so let's change the value here, we'll go 10000. There we are. So we've now got a low byte value of 0 and a high byte value of 1, but that gives us a decimal value of 256. So if this now went to 2, that would be 512. So whatever the high byte value is, we multiply that by 256, and then we just add in the low byte value, and that will give us our integer value again. So now as we look at the 9A and the 9B sketch, let's just stop the scroll on both of those. We can see now that I'm sending over here a value of 869. That's a high byte of 3, low byte of 101, and there we have the value of 869 appearing. So we are now getting the correct value coming out. Now, as you can see, the int was fairly easy to deal with, but what happens if that value becomes a long? Now, bringing over the trusty calculator, a long is made up of 4 bytes. Now, if we go to the Arduino reference, the high byte and the low byte function only work with 16-bit integers. So in other words, that will work with an int, an unsigned int, but it will not work with a long. So to break down the long, we have to use a slightly different method. Now this sketch has some bit shifting in it. Now sometimes when you first look at bit shifting, you can sort of think, on earth is happening here? But as I'm going to show you, it's not quite as complicated as you think. So I've got my long that has the value that we want to break down. And as we've seen from the calculator, we've got to break this down into 4 bytes. Now in the main loop, I have created an array called send array. It only needs to be a temporary array because it's going to get updated on a regular basis. Now, what then happens is when it is time to send my value, send array 0 has the value of my counter, and then we've got these 2 sort of angle brackets and a 24. Now that is a bit shifted value. So let's take a look at the language reference and see what is going on. So in the language reference, this is the standard Arduino reference, you can find these operators. There is a bit shift left and a bit shift right. Now at the moment we're going to be using bit shift right, so let's just click on that. And what this allows you to do is it allows you to move over the value a certain number of bits. Now if I bring up the calculator, what happens here, let's try and bring up the code at the same time. So now we have our code and our calculator, and here we have our long. This has 32 bits, so 8 bytes, 8 bytes, 8 bytes, 8 bytes. In our last sketch, the high byte was the byte here because we didn't have these 2 bytes. Obviously now our very high byte would be this value here, this byte here. But if you remember when we did the sketch where I tried to send an integer without breaking it up, it only sends the bottom byte. So when we bit shift by 24 bits, this value is all moved over 24 bits. So that one, if you moved it 24 bits, is going to finish up there. This one, if you move it over 24 bits, is going to finish up here. So that means that I can fill the first array element with this value that has now been bit shifted over here. Now at the same time, with the second element of the array, I'm going to bit shift it 16 bits. Now that's the second element of the array, and once again if I move it 16 bits, it's going to finish up here. The next byte, which is this byte here, we're going to shift it right again. So now we're going to get this part of the long, and finally this part of the long, I don't need to shift it, it's just going to read that byte regardless. Now once I've filled my array, I'm then running a for loop, and the for loop is just going to run through the array, all 4 elements, and it's going to serial.write those values across all 4 bytes, one after another. And then what I'm going to do is do exactly the same, but serial.print the binary values to the serial monitor. So I've uploaded the sketch and it's sending the data across. Let's just stop the scroll. And as we can see, I'm sending the value of 100034. If I just bring my calculator over, set it to decimal, clear everything off, 100034. Put that to the binary value. And we can now see that we have this value here. That is the binary value that I am sending across. Now, what I've then had to do is obviously to get that value into bytes, I've broken it down. So we've got the high byte, which in our case is a 0. The second byte is a 1, bringing back the calculator. The reason for that is this is the smallest byte. We then have 8 more characters that make up the next byte. Then the value of 1 is put in the following byte. So if we just bring up the code so you can see what's going on. In the array here, the third element is this value. The second element has taken this byte. This element number 1 has just got a value of 1, and because the number at the moment is so low that we're sending across, send array 0, the first element of the long, has a value of 0. So now coming back to the code window, you can see now that we've got our first element with a 0, second element with a 1, that next byte, the next byte, the total binary value looks like that. So you can see that if you like, this is the 1 plus then this byte will make this line of bits. The values that we're sending across, if they were decimal, would be a 0, a 1, a 134, and a 194. And those, when combined, are the values that make up the bytes that make up this long value of 100034. Now, we've seen how to, if you like, break down the long and send it across in bytes. Now we need to use the opposite function, the bit shift left. So this going to the reference is this one here, which now shifts the bits in the opposite way. So just as in the last sketch when we bit shifted right, we moved this byte across so many bits to get the value here. Bit shifting left does the opposite, where I can now take this value here, the lowest value, and if I bit shift it 8 bits to the left, those zeros will now replace those ones. If I bit shift it 16 bits, it's going to come over to here, and if I bit shift this value 24 bits, it's going to be moved over to here. So coming down to the sketch, this time we have to create an array for the incoming bytes. This time obviously it needs to be a 4-element array, and I need to have this variable, the incoming byte position, to keep track of where I am. We've got a long, which is my counter. That is the final value that we want. That is what we want, is the long that's sent from the first Arduino, received by the second one. Now, as before, we've got a variable, temporary variable, incoming byte, and I've also got a variable Q that you'll see why in a bit. So we now have our serial available, and as before, the incoming byte is going to be stored in that temporary variable. And just like before, I'm going to store it into the array, but this time, instead of it either being in position 0 or position 1, I need to fill up 0, 1, 2, and 3. So we're going to increment the value of the byte position, and when it becomes greater than 3, it's going to move that value back to 0. Once that's done, I'm going to serial print out the 4 elements of the array, and then we're going to build our long back up. Now, when you're new at programming, you can look at a line of code like this. Sometimes I remember when I started programming, I would look at someone's example and think, what on earth are they doing here? So let's break this down into little bits. So over here, we have our long, that is the final value that we're trying to get. We have our first element of the array, the second element, third element, and the fourth element. Now, the first element, we need to move it 24 bits over to the left. Remember from our calculator, this is the first byte, and I need this over there. However, to do that, I have to make the system think that my byte is now a long. So I put this long in brackets before the value, and it's called casting, and it sort of tells the system, yeah, I know this is a byte, start to treat it as a long. And you can see here that I've shifted that value 24 bits to the left to get that value in its correct position. Then all I'm doing is adding the next value, which has been shifted 16 bits to the left, and then I'm adding the next bit, and again these have been cast as longs, and then finally I've got the last byte that comes through, which is the one on the far right hand side. Again, this would be this byte that's arrived, and I don't need to bit shift that because that is the value as I want it. So I now add the 4 bytes together that have been cast as longs, and that will give me my final value for my counter. And then I'm just going to print out that value. So now we see our transmission and our receipt. Let's just stop the scrolling. And we can see here, let's just get these in the right position. There we are, 170. So we can see that our transmission was a byte with a value of 0, a byte with a value of 1, a byte with a value of 138, and this final byte had a value of 206. And here we see the received values. The total value that was sent was 101070, and when we put our bytes back together, when we bit shift them left, as we saw in that one line of code, we finish up with the same value for the long as the long that was sent. So at this point, we can now basically send any numeric value. Let's be honest, if you had a value that was larger than a long, and there are values that are larger than longs, you could just do more bit shifting to get that value broken down into more bytes. However, there is an issue that we now need to look at concerning the sending of these values. So if we go back to the sending sketch, the way this is working is I am sending a value every 1 second. Now I know that each of these bytes that get sent across takes just over 1 millisecond to send. So when I start the receiving sketch, the odds are that when I start the sketch, it will be in that gap between the last byte being sent and the first byte being sent of the next batch. But if I just show you a little diagram, here we have the code that we have just been sending. So we've got 4 bytes of data, A, B, C, and D. That's the highest value, the lowest value. Then I wait a second and I send the next value, wait a second, send the next value. Now that's easy with 1 second gaps. The odds of me starting the sketch in a position just after a byte has been sent and before the next byte has been sent are pretty good. Could you imagine if I was sending these bytes every 10 milliseconds? If I sent it every 10 milliseconds, the chances are that when I start the reading sketch, instead of it reading byte A as the first byte it receives, it might start reading byte C or byte D. But what it would mean is it would read 4 bytes, but they would be in the wrong order. If you like, they would be an accumulation of 2 sets of data that were sent, and that would give me a real mess, because when I bit shifted them all together, I'm going to finish up with completely the wrong value. So what we're going to do next is we are going to create packets of data. Now think of these as a data sandwich. So you've got your top piece of bread, you've got your filling, which is your data, and then you've got your bottom piece of bread. And these come over in a set order. Now the way we do this is we give the start byte, the one side of the packet, and the last byte specific values. They are always the same value. Now the packet start and the packet end should be different values, but the packet start for this packet will be exactly the same value as the packet start for the next packet, and the packet end value will be the same value as the end packet for any other byte. Now this becomes important, and if we go back to the webcam, these MP3 players require the data to be sent in packets, because otherwise they could receive an instruction where the middle of the play command becomes the beginning of the play command and the unit wouldn't know what it's doing. Also, these have a checksum which we'll look at in a bit, but let's have a look at how to build our packets first. So first we're going to look at the transmission sketch. So the sketch we've just done with those 4 bytes of data was version 10. We're now on to sketch 11A. Coming down to the loop, as you remember, we sent the 4 elements of the array. The difference is this time, when I set up the variables, I have set up 2 other variables. One is called packet start, and that's got a value of 255, and I've got packet end, which I'm going to give a value of 254. Now, your choice of these values, it's totally up to you. If possible, try and use values that aren't going to get transmitted too often, but if you've got a number that's incrementing, you are eventually going to send these values across, and that's why it's important to have a start and a finish. Now, coming down to the transmit sketch, before we just worked through the 4 elements of the array and sent them across. This time, when I start to do the transmission, I get my 4 elements of the array, and then all I do is I serial write the packet start, then I send over the 4 elements, and then I immediately serial write the packet end. And apart from that, there is no real other change in the send sketch. However, when it comes to the receive sketch, what I've now got to do is do a constant search to find a packet start and then build my array up and then look for the packet end. So let's have a look at how the code works for that. So for this example 11b, the first change is that that incoming byte array has been changed from a value of 4 bytes up to 6 bytes. So we've got 4 data bytes, and then we've got a start byte and a finish byte. I still keep the value of incoming byte position, and I've also put in my sketch the values of the packet start and the packet end, because I need these values to check against. Right. Coming down to the main loop, this is where things start to get a little bit interesting. So once again, our incoming byte is from the serial read, and I'm then putting that into the first element of the array. Now, if it is the first element of the array, the first thing that I need to do is check, is that first element of the array the packet start? In other words, looking at the diagram, is this the first byte, or have I started to read further down the data that is being sent? So we're going to do that check against the packet start. Is the 0 positioned byte the same value as packet start? If it is, we're going to increment the incoming byte position so that we then move on to the next byte. However, if the byte is not the right one, if we've got, you know, that in my diagram A, B, C, D, or even the packet end, then this will not increment. And so when the next byte comes in, it's going to put it once again in position 0, and it will keep putting the bytes in position 0 until it finds a packet start. only then will it start to build the packets up. Now this might seem a little bit stupid if we're just sending that transmission once a second, but if you've got data that's being sent every sort of 10 milliseconds or so, this becomes very important to making sure that your data arrives in the correct format. So then what we're going to do is, if it's not the first byte, so once we've got past position 1, position 0, we're then just going to keep incrementing, and we're going to fill all the remaining 5 parts of our array. Obviously, if that value gets to be greater than 5, we need to reset it back to 0, ready for the first part of the bytes of the data to arrive, which will be that packet start. Then all I'm going to do is serial print out the whole packet, including the packet start and the packet end, so that we can see what's going on. Then we've got some other bits that are going to go on here, because we've checked that we had the packet start. However, going back to our diagram, this is where things can get a little bit interesting. Let us imagine that element B has the same value as our packet start, because we're sending bytes. Now I've given the packet start a value of 255, but especially part D, if we're just doing a counter, part D is regularly going to get to a value of 255. So it would be quite easy to fool the system, and it would think that if it picks up packet D, that part D, byte D, that it then thinks, right, I've got the start of the packet, and it then starts working its way through. That's why we then have to do a check that the packet end is the correct value, because obviously if it started with D, thinking that it is the packet start, the packet end is going to be C, so it's a good chance it's not going to be the packet end value. Right, let's take a look at the code. So here all I'm doing is that quick check. Is the element 5 of the array the same as the packet end? So I've assumed that I've found the packet start. Now I'm just checking that I've got the correct packet end. If that packet end is correct, then once again I am rebuilding my long value, this time using elements 1, 2, 3 and 4. If you remember in the last sketch it was 0, 1, 2 and 3, and that's because element 0 is the packet start. And when it's all done, I'm either going to serial print out the correct value if it's got the right packet end. If it hasn't got the right packet end, I'm going to serial print out an invalid packet end, purely for this example. If you're doing production code, you do not want to be printing out lots of errors, because the time that it could take to print that out may cause you some issues with your timing. So now I have the two sketches running together. Let's just stop these at the same time, and we can see, if I can just get these two lined up, there we go. We have the values that are being sent. So those are my binary values, and the values that I'm sending over are 0, 1, 135 and 80, and when combined, once again, 100, 176. Now the received bytes, I have the packet start 0, 1, 135, 80 and the packet end. Now what I'm going to do, just to show you how this would work, if I now change this value to 253 and upload it, start the serial monitor, and as you can see, I'm now getting the same values, but because when it's done that end of packet check, it's going, I've got a 254 and I'm expecting a 253, I'm getting an invalid packet end message. So now we know that we are getting the correct bytes through. However, there is still one issue that we need to deal with. So we're now getting correct packets of data. If I just scroll this up, there is one other item that we need to think about. And that is, did these values transmit correctly? Now, if we go back to, I think it was 2 lessons ago, and the transmission type that we are using, let's just think a bit about how these transmissions are made. So if you remember from this diagram, we are sending literally a stream of zeros and ones. If you like, the wire, the output is going high, low, depending whether it is a 0 or 1. And if we go back to the reference, we start our serial with serial.begin and then the baud rate. Now the default configuration, so we don't tend to put the configuration in, the default is 8N1. Now this means that it adds a start bit and a finish bit to the data. So going back to my diagram, it adds an extra 0 or 1 at the beginning of or at the end of the packet. So instead of the packet being 8 bits, it's now 10 bits. However, as I said at the beginning, this transmission, it could be over fiber optic, it could be over Bluetooth, it could be over just a long wire. Just imagine that it gets some kind of electrical interference, or the Bluetooth gets messed up, and suddenly instead of that 1 being sent, a 0 gets sent. How do we know that the zeros and ones have been sent in the correct order? And to sort this out, we have to add what is called a checksum. So in its simplest form, we now have our packet start, our packet end, we have our bytes of data, and then we have a checksum. And the checksum, for this simple example, all we're going to do is add these values together and take the low byte value, because that's the value that will change the most. Now the reason for doing this is then when the data is received, we can do the same calculation. So mathematically, this value at the receive end should be the same as the transmission end. Now you'll notice it's only sending 1 byte. Why not sort of start adding everything together? Well, the problem is the more calculations you do, not only does it become slower, but the more data that you are then sending over. Now, if we're sending an instruction once a second, that's not going to be a problem. But if you want to start sending things every 10 milliseconds, if you have too many items in your transmission, it's going to take more than 10 milliseconds to send your transmission. So the checksum is a way of checking the data and making sure that we can pretty much say that that value is correct. Now, for most of our Arduino projects, a basic checksum will be fine. Those MP3 players use a very basic checksum in a similar format to the one that I'm going to show you in a minute. Obviously, if you are sending over something that is extremely sensitive, then you might want to do some more checks before you move something. You know, if you're just moving a simple servo on my model railway or something like that, I'm not really that worried if it was slightly out. But if you are doing something in engineering or something like that, you might need to be very, very careful to make sure that you get the right values. And again, depending on the chances of interruption or interference on your transmission, that should also be something to think about on your checksum design. So this final pair of sketches we're going to look at are serial version 12A and 12B. Let's have a look at 12A to start with. 12A being the send. So as before, we've got our packet start and our packet end. All of this code remains basically the same as before. It's only as we come down to our sending where in the main loop I've now added a new variable, send checksum, which is a byte, and I've also got an integer which I'm making sure is set to 0 every time the loop runs. So as before, we've got our array that we have created from our long. Nothing has changed there. I've also sent my packet start. So we've got the packet start has been sent as before. We've then sent the 4 elements of the array, but as it's sending the elements of the array, it is incrementing the value of checksum. So it's checksum plus, so it's checksum equals, that plus or equal means it's the equivalent of checksum equals checksum plus this value. So it's adding all of those 4 values together. Once it's got that, it's going to serial print it out so that we can see it. And then because it's just creating an integer, I am going to take the low byte of that checksum. I'm then going to transmit that low byte, and then I'm going to send the packet end. So now as the code starts to run, let's just stop the scroll. We've got our 4 bytes, which are 0, 1, 135, and 39. Those values added together give a value of 175, and the value that we're actually sending over is 100135. But now what we need to do is take that checksum and, if you like, check it on the receiving end. So the receiving sketch, the 12B sketch, once again, I've had to increase the size of the receiving array because now we're receiving that extra byte that is the checksum. So once again, when the first bytes come in, the first thing it's doing, as before, it's looking for the packet start. Once it's got the packet start, it proceeds as before, and this time, instead of taking just the 5 bytes, we've now got 6 bytes coming in, which are the 4 data bytes, the checksum, and the packet end. And then, just as with the send sketch, what I then have to do is work through the values of 1 to 4, which are my data bytes. And once again, I add the values together. This time I've done it checksum plus just to show you the alternate way of writing it. So I'm now adding all those values together, and then I'm getting the low byte of that value again, which gives me send checksum, and that value should be equal to the byte in position 5 in my array. And if it's not equal, that's what that symbol is, not equal, then we're going to serial print an invalid checksum. Once again, I'm still keeping the invalid packet end and all the other code from the previous sketches. So here we have the 2 sketches running together. Let's just stop them both. And we can now see that if I just get these ones lined up, where are we? We've got a value of 10358. So let's move back up. 10358. So to get that value of 10358, we've got to check some value that I transmitted of 143. And we're receiving a value of 143. I've got my packet end is correct, my packet start is correct, and as you can see, the values both equal each other. So we're getting a successful transmission. We now know that the bytes are in the correct order because of the packet start and the packet end, and we can now virtually eliminate any chance of data corruption in the transmission because we have the checksums that equal each other. Now you may think, what a lot of faff to get this thing working. But if we look at this MP3 player here, I just want to show you how they transmit the data. This is done over serial. It's just exactly the same as we've been doing. But as we look at the configuration for the transmission, in their system, they've got a start code, a command type, a data length, a data 1, a data n, and a checksum. Now, that start code, that tells them this is the beginning of the transmission. They've got a checksum at the end rather than a packet end. So they've structured the packet slightly differently, but it's the same idea. And if you look at their check bit system, it's the 8 bits of the sum of all the bytes when the code has been added. So if you like, they add all these bits together and then they take the low byte out, just as I've been doing the low byte, and that gives them their checksum. So coming back to our diagram, we now know that we have a valid start to the packet. We know that we're getting the data in the right order. We now know that we can check that transmission to make sure that we have not received any corruption of the data through interference or any other means, and we have the correct end of the packet. Now this is really useful because what I'm going to do in the next lesson is we're going to start communicating between not just 2 Arduinos, but we're going to look at how we can transmit between 3, 4, 5 and quite a few more if we need to, in which case we definitely need to know that our data is in the correct format. So quite a lot of information to take in today, but hopefully by the end of the lesson you now understand how the data packets are formed and also the importance of error checking. Now in the next lesson what we'll start to do is connect up a few Arduinos together, not just a couple. I think we should add 3 or 4 and start communicating backwards and forwards between multiple Arduinos. So we'll do that in the next lesson. So thanks again for watching, and please click the like and the subscribe because it really does help the channel. Thanks again for watching. See you in the next video. Bye for now.